This video is going to cover forces and go a little bit more in depth into some of the forces and some of the free body diagrams that we've been doing recently. So first of all, some of the forces. We mentioned these in class the other day. We've got gravitational force, we've got normal force. Normal force is kind of like a support force, like a box sitting on the table. When you have a normal force, it is always perpendicular to the surface. Then we have also frictional forces, which is air resistance or static and kinetic friction between surfaces. We will get to that more in depth in the next video. Tension is also a force. Hanging or pulling from a cable or a string, that tension is always directed in the parallel to the rope. And then we have spring forces. Spring forces we'll get to later in the unit. So another thing to think about is these words static and kinetic, because we talk about friction, which we'll get into more in the next video, but when we talk about friction, we talk about static friction and kinetic friction. Static friction is like when something is sitting still and it's not sliding down. Kinetic friction is when something is sliding, how much force is stopping it, the kinetic friction that's slowing it down. Okay, in this video though, we're going to focus more on things like weight. Another way to talk about weight is the force of gravity. So the magnitude, that means the amount of the gravitational force acting on an object of mass, is the force of gravity, also called weight. And our formula for this, F sub g, is equal to mass times gravity, where g is the acceleration of gravity, or negative 9.8 meters per second squared. Sometimes we also use the abbreviation acceleration due to gravity. So you might see a capital G or you might see it as A sub G. Okay, the difference between mass and weight. Mass is a scalar quantity. It is the amount of matter, how much stuff you have, and it is measured in kilograms. Whereas weight is a vector. In other words, it has a direction, and it is typically, when we talk about weight, we are talking about the force of gravity acting on a certain mass. So you in your body have a certain mass of kilograms, but when you add gravity to that, now you have an actual weight to it. Weight is a force and therefore a vector quantity. What will be the direction of the weight vector in all free body diagrams? We will always draw our vectors straight down with force of gravity. That is always going to be the way we go, straight down, because that's the way that gravity always goes. Gravity is always straight down. All right, what about some calculations? If we have a 10-kilogram object on the surface of the Earth, how do we figure out the weight of that? Well, again, weight is like force of gravity, and so we would just take 10 kilograms times gravity, and that's going to give us negative 98 newtons. So that's just a real basic calculation there. What if, though, we take that object and we go to the moon? Where on the moon, the gravitational pull is 1/6 that of the Earth. Well, if the gravitational pull is only 1/6 of what we have on the Earth, then we're going to take its weight on the Earth and we're going to divide by 6 or multiply by 1/6, and that's going to give us a negative 16.3 newtons. So whereas something weighs 98 newtons on Earth, on the moon, it only weighs negative 16.3 newtons. And so you've seen some images of like the astronauts on the moon and things happening on the moon. And I think you have an understanding of things weigh less when they're on the moon. Is their mass different? No, it is the same exact amount of mass, but something that's really heavy on the Earth is not going to feel quite as heavy on the moon. All right, let's talk a little bit more about contact force. The normal force, which we normally abbreviate as F sub n, that's where we are going to use more in this class. Sometimes in our textbook, they might use just a plain old n, but we use the F sub n in AP. This is an AP thing, so we'll use F sub n in AP. Normal force is a contact force. In other words, it is something contacting, it is touching each other, and that is exerted by a surface on an object, and it is directed perpendicular to the surfaces in contact. Okay, we talked about this a little bit the other day, but let's just go ahead and do an example. Draw a free body diagram for the forces acting on the box and then solve for the value of the normal force. So if we have a box, and let's say our box here is 5 kilograms. We have a box. We have the force of gravity acting down on it, and then we have this counteracting force called the normal force. When you draw your vectors, the normal vector should be the same length as the force of gravity. So how do we calculate that? Well, the force of gravity is mass times acceleration. So that's 5 kilograms times the force of gravity. That's a negative 49 newtons. That's going down. That's why it is negative. But the normal force goes the other way. So the normal force is a positive 49 newtons. We've done things like that a little bit in class before. So what would happen if a person pushed down on the box with a force of 20 newtons? How would the free body diagram of the forces acting on the large box change? And then how would the normal force change? Okay, well, let's go over to our diagram and let's draw our free body diagram. We are going to have the normal force. So my gravitational force is this long, and on the other page we figured out that that was 49 newtons, and it's negative because it's going down. Okay, what if someone pushes down on the box with another 20 newtons? Well, we need to somehow fit it in here. I think I'm going to try to fit it on the right-hand side of this. I'm going to have a 20 newton, not quite half as much. This is going to be the applied force, which I'm going to abbreviate F sub ap for applied. And that applied force is 20 newtons. Then my normal force, this box is not breaking through the table yet, so my normal force has to counteract both of those forces. So my normal force is going to be much longer. So if we start with the conception that the sum of the forces in the y direction is equal to 0, if we look at our free body diagram, we have the force of gravity, we have the applied force, and we have the normal force, and all of that's supposed to add up to 0. I realize now that my applied force should be negative because it is pointing down. You're pushing down on the box. So if you're pushing down on the box, that is a negative force. So my gravitational force is negative 49 newtons. My applied force is negative 20 newtons. And that, if I subtract my normal force to the other side, that's going to be the opposite of my normal force. And so if I add these together, I come up with a negative 69 newtons is equal to the negative of the normal force. And so that means my normal force is a positive 69 newtons. In other words, the normal force, that supporting force, now has to support that push. The person is pushing down on the box. So we have to support that as well. So our normal force is a total of 69 newtons. What about tension? Okay, what if we have this same box and this time we are attaching a cable or a rope to it and creating some tension? Well, let's go ahead and draw our free body diagram. From before, we have the same 5 kilogram box. So from before, we do have the the force of gravity, which is a negative 49 newtons. Now we're starting over. We don't have that 20 newtons from before. We're starting with just a blank box again. And this time we have a cable attached to the top, and it's pulling up with a force of 5 kilograms. This is the force of tension, which is 5 kilograms. So then what is the normal force? Well, once again, our normal force, our sum has to be 0. They have to add up to 0. So we have the force of gravity, we have the force of tension now, and then we have our normal force. Our normal force is always acting upwards. But this time it's not going to be exactly equal to 49 because we have this 5 kilogram tension, which is kind of easing the job of the table, right? The table has to support it. Well, if I pull up with 5 newtons, it's going to make that a little bit easier. So my force of gravity is negative 49 newtons. My force of tension is going in the positive direction. It's going up. So it is, I was about to write 5 kilograms. I don't need to write 5 kilograms, do I? Because it's a 10 Newton. I need to change that tension to 10 Newtons. I'm going to erase this one. So I need to change that to 10 Newtons. The force is 10 Newtons. So our tension is 10 Newtons going in the positive, the up direction. And we have the normal force, and that's what we're trying to solve for. So if we're trying to solve for this, that's supposed to be a 0. If we're trying to solve for this, I could say that becomes negative 39. And I could subtract my normal force to the other side. And so now it's negative because I've subtracted it. So that means the normal force is 39 newtons. So that tension pulling up has eased the job of the normal force and made the normal force lighter. That actually ties in very well with our next concept. Our next concept is what we call apparent weight. Sometimes it is called apparent weight. Sometimes it is also called the normal force. Let's talk about it. It says an object's true weight is always equal to mass times gravity. If something was placed on a scale and then the system was allowed to accelerate upward or downward, the reading on the scale would not equal the true weight of the object. So the apparent force, what we call the apparent force or the apparent weight, is the normal force. Or in other words, it's the reading on the scale. So here's an example. We have a 5 kilogram block. We put it on the scale. What is the reading on the scale in newtons? So I think you all know what a scale looks like and everything, but I'm just going to draw one over here. So here's my scale, and here is my box. So I'm just drawing this box over here so that you can see kind of what it looks like. We have been talking about the forces are equal to 0, and that's when things are not moving, when there is no acceleration, or if it is a constant speed, which would also mean no acceleration. So now I'm going to look at, instead of setting it equal to 0, I'm going to go back to our equation on our equation sheet, which is F equals ma. I'm going to call this the sum of the forces, and that g should be like a little subscript g. The sum of the forces of gravity in this case is mass times acceleration. So the force of gravity is 5 times negative 9.8 meters per second squared, which we multiply that out, we get negative 4.49 newtons. That's the force of gravity. If that's the force of gravity, then the scale is going to read positive 49 newtons. That is the normal force, and the normal force and the reading on the scale are the same thing. All right, well, what happens if we take that block and scale and we start moving them? We accelerate them upward. For instance, maybe you're standing on an elevator and the elevator goes up. And I think you know when that elevator goes up, you feel different. You feel a little bit heavier. So we're going to investigate that a little bit. So if this is going up, the whole system is moving up, what is the new reading on the scale? Well, I think you know how a scale works. I hope you know how a scale works. It's like it's got a little spring in here and it's reading the pressure. Well, if the scale is being pushed up, then that's going to compress those springs more, and the reading is going to be higher. Okay, let's think about this. So in this case, again, we're going to go back to the sum of the forces. This time it's not equal to 0 because we're moving. It's equal to mass times acceleration. The normal force is going to be going up. Let's go ahead and draw another diagram here. So again, we have our scale, we have our box, we have the force of gravity, and we have our normal force. But this time with that acceleration, that's since it's going against gravity, it's basically adding to the gravity. So let me try to hopefully explain this a little bit better. Okay, so on our diagram, we have the normal force pointing upwards. We have the force of gravity pointing downwards. And we also have this acceleration going on, which is basically making our gravity heavier in a way. Okay, so this extra force is going to be added this way, which means that our normal force is actually needing to be a little bit taller than we had it before because we have this push going against it. Let's look at the calculations. Our normal force is going up, so I have it on one side of the equation. Our other ones are going down, so I have those on the other side of the equation. So our normal force is what we're trying to find, the reading on the scale. We know that this one is 49 newtons because we had found that before. 49 newtons. Plus we have this acceleration going on, this elevator, which is adding some apparent weight to what we're doing. How much? Well, mass times acceleration. The mass is 5 kilograms. The extra acceleration is 2 meters per second squared. So we're going to add those together and we're going to get a total of 59 newtons. So you stand on the scale, the elevator goes, and all of a sudden where you used to be 49 newtons, suddenly now you are 59 newtons because the elevator is pushing up on you with the acceleration. That only happens while the elevator is accelerating. We will do this. We're going to get on the elevator in class, so you can hopefully see this a little bit better and maybe get a better grip on what's going on. All right, well, what happens when the elevator goes down? Well, again, I think that you have experienced going down on the elevator and the way it feels. Hopefully you can also imagine if you have your scale and you have your box and suddenly the elevator goes down, it's going to drop that scale down. And so now you're going to appear lighter because the scale is dropping. And since it's going in the same direction as the gravity, it's like easing off a little bit of that. So now I'll draw another free body diagram. We have our normal force acting in the upward direction. We have our gravity acting in the downward direction. And now we have the acceleration dropping. And so it's basically it's easing the tension of gravity. It's not going as, gravity doesn't seem as intense when it goes down. And so since gravity is not as intense, it's almost like you're weightless for a minute. It's easing up on the normal force. So what's happening is you have the 49 from before, and this time we're going to subtract. Since it's going downward, we're going to subtract that quantity from it. And so now we're down to 39 newtons when you're going downwards. I think we should maybe write something in the margin here, if we can find some space somewhere in the margin. The apparent weight, or the normal force, is going to be less than the force of gravity when the acceleration is down. But the normal force is going to be greater than the gravity when the acceleration is going up. And again, we will get on the elevator and test this out so you can feel it and see what's going on. That is the end of today's lesson on forces. We will get into friction in the next section, but for now, this at least has given us a little bit to think about with some motion involved with our normal forces and with some different forces, whether they be tension or applied forces, that are also involved.